Hi everybody, this is Mr. Folly, and welcome to our brand new topic 6.1 heat. We finally are going to change a little bit and not emphasize the mole and those calculations as much as before. So we're onto a brand new learning experience. So we've got quite a few things to go over in this one. Heat versus temperature, heat flow, energy of a phase change, energy of different states of matter, boiling versus evaporation, which are very different. It's very important to know that those are different things. Qualitative versus specific, or qualitative specific heat, so an explanation of what specific heat is. And you need to know that water is a very high C, which is a specific heat. What a dumb letter choice for specific heat, but that is what it is. Temperature is the average kinetic energy. So it says Boltzmann distribution. So there are two things for a Boltzmann distribution. This is the number of particles, and this is their kinetic energy. Remember, kinetic energy is the energy of motion. So in a drawing like this, I can tell that there's a peak right here, and that peak would indicate the average kinetic energy. I could have a different one that has a slightly different peak, and so on and so forth. So this has a different peak that's farther on. Now notice the hump is lower and it is farther to the right. The red one is hotter and the blue one is colder. And the reason why, oops, that's not blue. The reason why the red one is hotter is more particles have a higher average kinetic energy. So temperature is your average kinetic energy, which is represented by the peak of the little hump there. So a high temperature would be a lower peak farther to the right. And a low temperature would be a higher peak farther to the left. Heat is total kinetic energy. So total kinetic energy means that there's at least two factors. And your two factors are temperature, which is your average, and the other thing that impacts it is the mass. So that means that mass and temperature both play a role. So what has more heat? A drop of boiling water or an ice sculpture of me? Would I give a choice where I'm not the right answer? I doubt it. The ice sculpture of me would have more heat. Why? It's not just an ice sculpture of me, a giant ice sculpture of me. So I suppose I should be blue. There I am. Smiling as always, a little periodic table in hand. Okay. So I would have a higher heat because I have more mass. Han Solo's donkey or Han Solo's tauntaun. Now, I don't know if you remember this or not, but Empire Strikes Back, best Star Wars movie. Han Solo, he had to ride around on these weird-looking critters that looked like giant rabbits. But they had giant legs. And he rode on them with a little saddle. And he'd run around in the snow. And then when he got trapped out in the snow, looking for Luke Skywalker or some nonsense, he had to take out his little lightsaber. Yeah, you were waiting for the special effect noise, didn't you? And he took his knockdown tauntaun. You know, I had every intention of actually getting a picture of this thing from the internet. Cut it open. And he had to get his sad self, we'll make his sad self gray, hanging out inside the tauntaun to stay warm in the terrible, terrible night of whatever that crazy planet was. So what would have more heat? A little donkey, hee-haw, hee-haw, or a big tauntaun? It would be the big tauntaun. Why? Because tauntauns are large animals, so you can hide your body, and if you have a little donkey, you can't stuff your whole self in there. Actually stuffed himself in there, and some of those of you who are looking for extra credit, he also stuffed Luke Skywalker in there too. And he survived, of course, after sitting in the warm water for a while. A match or the planet thingy Pluto. It used to be the planet Pluto, now it's a planet thingy Pluto. So what would have more temperature, or what would have more heat? Pluto would. Why? Because it's bigger. Even though it's not a planet, because it's too, I don't know, piddly small to be a planet, it's still way larger than a match. So I also want to point out something. Heat and temperature are not opposites of each other. What has more heat? A big fire or a small fire? Which one would have more heat? A big fire has more heat than a small fire. What would have more heat? Olympic swimming pool at 80 degrees or an Olympic swimming pool at 70 degrees. Which one would have more heat? The one at 80. So they're not opposite of each other. You just try and use the exceptions to prove the rule. Heat flows from hot to cold. Hotter particles move faster, so they dictate the movement. If you touch an ice cube, so pretend here's a little ice cube, here's a little finger. When you touch it, your heat flows into it. So the reason why you feel cold is because it's stealing your heat, which sounds cold just talking about it. If you boil water, the heat goes into the pot, not the cold into the flame. This is always true. So things always flow from hot to cold. So now I believe a phase diagram for constant heating. So if I take a block of ice at -20 and heat it over a Bunsen burner. So what I'm going to do is start out right here at -20. And, whoops, I'm going to call this -20. And this is going to be time 0. And time is going to end up here until time final. So this is time. This is temp. So as I heat this at -20, it's going to get warmer and warmer and warmer and warmer, and then it stops getting warmer for a while. It stops getting warmer at the magical temperature of 0 degrees Celsius. That is where this guy melts. Then it starts getting warmer and warmer and warmer again. It cannot be 0.1 degrees Celsius until it is a liquid. Okay. So, and then it plateaus. And that would be at 100 degrees Celsius. And guess what happens there? Boils. And then, and it's going to keep getting hotter and hotter and hotter and hotter and hotter and hotter and hotter. So, and this is where it's going to be gas. So, if you look at this, the temperature only changes when you're a pure solid, a pure, or liquid pure, I'm talking funny, or a gas pure gas. When something is melting, it actually is both solid and liquid, and they're going back and forth. It's said to be in equilibrium with each other. This would be a liquid to a gas, and a gas to a liquid. They're in equilibrium with each other. They're going in and out. If you keep adding heat, eventually you're going to end up with more gas particles than liquid particles, and then you're able to raise your temperature again. So what's happening here, one more annoying color, is when temperature is going up, right, temperature is increasing, that means my kinetic energy is increasing. So I'm heating this thing under a flame, so it makes sense when the temperature is increasing. But why is it on my little plateaus here, the temperature doesn't increase even though I'm adding energy? The reason why is that energy goes into the phase change. So the energy goes into the phase change, which is not kinetic energy, but potential energy. Okay. So if I were to ask you, where does the potential energy change in a phase diagram, you would say the potential energy changes where the phase changes during melting or boiling. I'm going to draw another quick little one of these things. And I mean very quick. The only difference is I'm going to start at hot and go to cold. Okay, so again, this is temperature, this is time, so this would be cooling something. And so again, this would be a gas, this would be a liquid, this would be a solid, this would be condensing, and this would be freezing. I also want to point out that This area right here is longer than this area right here. The reason why is it takes more energy to change from a gas to a liquid than a liquid to a solid. All right. So different states of matter have different energies. Temperature is your average kinetic energy. The state of matter is irrelevant. States have different potential energies based on bonds. Solids are close together, they have stronger bonds. Liquids are pretty close together, they're weaker bonds than solids, but still pretty strong. I almost spelled pretty wrong. Pretty strong. Gases are extremely far apart, so there's almost no bonds, which means they're the weak. Bond energy is due to position, so the closer you are, the stronger you are, as long as it's set up that way. A couple of questions how this works. You had to hit pause. Which has higher kinetic energy and which has higher potential energy? A helium balloon at 0 or ice at 0? Kinetic energy for these would be equal. Why? The temperatures are the same. Which would have a higher potential energy? Helium has a higher PE. Why? Because it's a gas. Ice has a lower PE. Why? Because it's a solid. Oxygen at 10 or solid copper at room temperature. So here we've got 10 and 25. So the copper would have a higher kinetic energy. Why? Because its temperature is higher. And then for oxygen, it would have a higher potential energy. Why would it have a higher potential energy? Because it's a gas. A cup of water at 75 degrees Celsius or Lake Michigan at 75 degrees Celsius, kinetic energy is equal. Why? Because the temperature is the same. That doesn't equal 0, I'm sorry. Kinetic energy is equal because they're the same. And then potential energy is equal because both water. Good. Boiling and evaporation are very different. Boiling is a liquid going to a gas. Evaporation we know is liquid going to a gas. But some very important things happen here. One of them is at the boiling point or below the boiling point. Evaporation happens below the boiling point. You do not cook your macaroni and cheese in evaporating water. That would not be hot enough to cook your macaroni and cheese. Sweat does not boil off of your skin, meaning it gets to an unbelievably hot temperature and makes you shriek like a little girl. Boiling occurs throughout the liquid, so if I have a pot of water that's boiling, boil. The boiling takes place top left, middle, bottom left, bottom right, here, all at once. Okay. I know they'll be a little bit hotter on the bottom, but if it's the same temperature, the boiling would happen everywhere. Evaporation occurs only at the surface. So let me give you a quick rundown of evaporation. Using the same little pot of water that I have over here, what happens is some of the particles have enough energy to actually break free and turn into a gas. They have enough kinetic energy. Remember the little Boltzmann distribution thing? The guys over here have enough energy, but you can't just turn into a gas if you're surrounded by liquids because you're so tight that you cannot spread yourself out enough. So you have to be at the surface so that you can break free and get through there. Evaporation is a cooling process, so the hottest particles leave, so the remaining liquid is cooler. So this is why sweating works. Blue person here, pretend they're hot. They've got sweat on them, of course, accumulated under the armpits. We'll say around the neck even. And what happens is the hottest of these particles leave. So if the hottest of these particles leave, that means that it's taking heat away with it. So if something is taking away heat from you, that's making you cooler. That means you get to survive. Oh, yay. If it doesn't take the hottest particles away, that means you overheat, and the heat stays with you, and you are one hot, overheated, passed out, dying person. Boiling, melting, etc. occur at temperatures different than 100 degrees Celsius and 0 degrees Celsius. Alcohol boils earlier. Oxygen boils earlier. Copper freezes at a warm temperature. Oxygen boils at something like minus 200 degrees. Alcohol boils at something like 77 degrees. Copper freezes at a warmer temperature, like 2,000 degrees. Copper will freeze at 2,000 degrees Celsius. That's why we don't see liquid copper very often. So we have it in our head that things freeze and melt at 0 and 100. That's only true for water. And also pressure messes with that, but that's a much later chapter. Substances change temperature differently depending on their identity. So the ability to change temperature is called specific heat, and it is abbreviated C. I have no idea why. On a hot summer day, see if you lived in Indiana, a hot summer day, you run around barefoot like the hillbillies. And on your hot summer day, you're walking around on your blacktop driveway, and at 2 o'clock in the afternoon, your sad little feet start to burn on your blacktop. Ah, oh no, ouch. And you don't have shoes because you live in Indiana, so you decide you're going to run into the grass. Now, at 2 o'clock in the afternoon, both the grass and the blacktop are the same temperature. They're both, say, 100 degrees. But the reason why the grass doesn't hurt as much is the grass cannot impart its heat into, I should use red there, cannot impart its heat into your naked feeties as well. So, because blacktop can convey its heat quickly, it will hurt, and because grass doesn't convey its heat as well, it will not cause that heat to come into a painful degree. Okay. By the way, part of this is because grass has water in it, and water has a very high specific heat, and a high specific heat means that it will change temperature or give its energy slowly. The great movie, what was a great movie? The one with the Red Ryder BB gun where you shoot your eye out. Christmas Story, that was it. So in Christmas Story, there was a kid that kissed a metal pole in the winter. Because metal changes temperature so quickly, when the kid kissed the metal pole, of course I should have made it blue, when the kid goes to kiss the metal pole, what great lips he has. So he goes to kiss the metal pole, looks like a beak. That's a nose right there. Isn't that something? What happens is it absorbs so much of the heat right away that the lips become cold enough that they actually freeze the saliva right onto it. So that only happens because a metal pole has a low specific heat, or a low C, so it'll absorb enough heat from the lips to freeze the saliva on there, and you're stuck on there. Wood, which has water in it, has a much higher specific heat, so if you kissed a tree, you wouldn't have those same problems. So remember, if you're sad and lonely and it's frozen outside, you can always kiss a tree and not be stuck. Don't kiss the metal poles. Last example of specific heat is if you cook a turkey, if you preheat your oven to 450 degrees. It's Thanksgiving time. So cooking your turkey to 450 degrees Fahrenheit. If you preheat your oven, the air inside of your oven is 450. The trays in your oven are also 450. If you stick your hand inside the oven, it feels warm. You may not find it very comfortable, but it's kind of warm. If you take your hand and actually touch the trays, again, draw your little finger touching the tray, what happens is the heat from the tray goes into your finger much, much faster, so quickly that it will burn your fingers. Now the air particles are also going to convey their heat to your hand, but it's so slow that it doesn't cause the pain and the damage that touching the metal will do. So why is it you can put your hand in the air and it doesn't hurt? Because the heat is conveyed slowly, which means it has a high specific heat. If you touch the metal, it has a low specific heat and conveys the heat quickly. Water is a very high specific heat. That's why it's used to cook food, meaning it can hold a lot of energy, so it can release a lot of energy. The lake effect. The lake effect, people think that's only one way or the other. In the winter, because Lake Michigan is so slow in changing its energy, in the winter, the lake is 3 months behind as far as temperature goes. So in the winter, 3 months behind means it's warmer. In the summer, it's still 3 months behind. So in the summer, if you're 3 months behind, instead of being 100 degrees, you are 70. And in the winter, instead of being 0 degrees, you are 40. That keeps Chicago in its wonderfully moderate climate. Metals have a low specific heat, gases have the highest specific heat. I'm going to put this review thing up here again instead of just reading it to you. But the conference I went to that I skipped school for on Thursday, why did Leonardo DiCaprio die but Rose lived in the Titanic? The reason why is, you know what, that is our extra credit question for tomorrow. That way I can get out of here in under 21 minutes. Have a good one. I will see you tomorrow in class. Bye.